Welcome to the next session of this course. Today we will learn about different ways to quantify the scattering as well as absorption. Till now we have learned about that if you shine a light like this onto your tissue, so you have the source and you have the detector, and you shine the light like this, so it will interact with the tissue. The tissue is the central part, and then the light which interacts with the tissue can actually undergo either an absorption or it can go through scattering. Okay, these are the two major principles that occurs within this tissue, and you will see these things happening, and then some part of it will come out of this detector. Okay. So in today's session we will try to understand how do you actually quantify the absorption coefficient as well as the scattering coefficient. That is a property of the tissue. So we will talk about absorption coefficient and scattering coefficient. So mu sub A is known as absorption coefficient, and mu sub S is known as scattering coefficient. Okay. So let us talk about a tissue. So when we talk about a tissue has many tissue constituents. A very simple way to work about this mathematical model would be to come up with the tissue constituents as a spherical particles. So let us assume that the tissue constituents are having spherical particles. So tissue constituents are nothing but spherical particles. Okay. There are lot of numbers of particles or tissue components within a particular tissue, but let us simplify this problem to that the dimension of that particle is kind of uniform throughout this tissue constituent. So what we can assume is that the radius is homogeneous, means all the particles are having the same diameter throughout the tissue. Okay, so that is a simple assumption that we have taken, right? So now how many number of particles we have? We have n number of particles. Right. Now from this n number of particles we have to simplify it even further, right? How we will simplify? What we will say is that instead of taking all the particles in the tissue, okay, what I will do is that I will take only a single particle. So let me take a single particle and try to analyze what will happen if the light actually passes through that particle or the molecule. Okay, so I am going to take that single particle now, a single particle or single molecule or a molecule. So now my analysis would be on this single molecule. If I shine a light, what are the things that could happen, and from this single particle can I actually go to large number of particles. Okay, so from a single particle I quantify something for a single particle, and then I go ahead go back to my hypothesis of large number of particles within the tissue with the same diameter. Okay, the same diameter, and and then I do something in the mathematics so that it, instead of single particle, it will represent n number of particles. Okay, using number density. So to start off with, let us start with quantifying. How do we quantify the absorption property of the tissue? So the absorption property is given by absorption coefficient. Okay, so we will try to understand how do we quantify the absorption coefficient. Now, as I said, we have moved from a many particles to a single particle theory. Now, let us talk about a single particle. So, this is a single sphere of particle. Now, what I am going to do is that I am going to shine a light source like this. Okay. So, this is the light source that I am shining. Okay. So, this is the light that I'm going to shine, and now and these are the all the lines that you see over here are the photons. Okay, this is the photon number 1, this is 2, this is 3, this is 4, and so on and so forth, n number of photons. Okay, so what is happening is that the photon number 1 is not having any interaction with this molecule, right? So it will just pass through over here. Okay, and what you are doing is that you are having a detector over here on the other side. Okay, the molecule 2, the particle, the photon 1 will directly pass through this and it will get detected. The photon number 2 will also pass through because it's not interacting with this molecule. Photon 3 also will kind of pass through, just graze on the surface, but it will kind of pass through this molecule. Now, what will happen with photon 4 is that it will see how much is the thickness of this particular tissue that it is interacting. If that thickness is kind of significant, then it will absorb, but if the thickness is not that significant, that will also kind of pass through. Okay, but now if you see that this thickness of this molecule is now quite significant, so assuming that it will not pass through, it will just absorb over here. Okay, similar to this photon, this will assume that this will pass through, and then the remaining last 3 photons will kind of also pass through. Okay, so now what do we observe? We observe that there are 2 things. The first thing is the geometrical cross section of the actual sphere, that is the area observed, or the area, the cross sectional area of this sphere. Okay, so that is known as geometrical cross section. Okay, so this is the actual cross section of your sphere. It would be a kind of a circle. So if you say it's the area, it's like pi r square, right? But what if you see is that the light actually does not pass through completely in that circular cross section, right? You see that over here, this photon as well as this photon passes through. So there is effective cross section, right? There is effective area where the there is actual blockage of light source, right? So this area is defined by, let me use this orange color, right? So this area is defined as effective cross section. Okay, this is an effective cross section. So this is the effective area that the light is being blocked. Okay, this again is kind of a spherical area, pi r square, right? So this is known as effective cross section. Fine. So both of them are different. Geometrical cross section, as you see, is the actual cross section area, but once the light interacts, or once the photon interacts with this particular molecule, you will see that some regions in the top and the bottom, it actually, or on the surface, it actually allows the light to kind of pass through, and so the actual effective cross section area would be kind of lower as compared to the geometrical cross section. So here you can, if you kind of see, the geometrical cross section area would be far more than the effective cross section area, right? Now, so now how do we define like how much of the okay, so let me just first define the geometrical cross section area. So geometrical cross section area is defined by A, and effective cross section area is defined by sigma A. Okay, sigma of small a. Okay, sigma of small a. Now I want to find out what is the relationship between effective cross section area and geometrical cross section area, right. So the way they both would be defined are sigma a is equal to actually qa into capital A. This qa is defined as absorption efficiency. Okay. So at a later stage we will talk about how do we quantify this absorption efficiency, and we talk about scattering, we talk about scattering efficiency, right. So we will talk about Rayleigh theory, my theory, and how do we quantify this absorption efficiency for a particular particle with a particular dimension, right. So that we will talk about at a later stage, but as of now we define what is the relationship between the actual geometrical cross section area and the effective cross section area, right. So QA is kind of one of the more important part of the mathematical approach. How do we find the bulk absorption coefficient, right. So if you remember, our main objective is to find the, so if you remember, it's very important to know that our main objective is to find mu a, that is the bulk property, bulk optical property, right. So for that what we do, we assume that instead of tissue constituents of various dimension of particles, we assume that all the particles are of same dimension, right. And then instead of all the particles, we talk about a single particle, right. And then we say that if the light shines through that single particle, what will happen, right. So we came up with geometrical cross section area, effective cross section area. The next thing is to find out how do you define the sigma a, right. So one way is to define your sigma a is what I have already defined over here. Sigma a is equal to qa, that is the absorption efficiency into the cross sectional geometrical cross section, right. Another way to define the sigma a would be, that is the effective cross section would be defined as power being absorbed by incident power. Okay, so where P absorbed is given as absorbed power and I naught, so this is in watts, I naught is given as intensity of incident light source or incident beam of light. Okay, this units, if you see, it's actually watt per centimeter square. So if you see, the power is in order of watts and units, this one is watts per centimeter square. So if you find out this one, that you will see that it is in, it actually makes sense, because this effective cross section area is also in order of centimeter square. Okay, this will become more clear once we do some kind of examples to find out absorption cross section, effective cross section for a particular diameter. Okay, so this is another way of finding the cross section area, effective cross section area, that is how much is the power absorbed by the incident power, incident light intensity. Okay. Now as I said, we have to now move from single particle, we have moved from many particle theory to a single particle theory. Now we have to go back from a single particle theory to a many particle theory. So for that, what we need to do is that we need to introduce one parameter known as rho, which is known as the number density. Okay. So now we have calculated for a single particle. Now we want to move for a many particle. So we introduce something known as number density, which is defined as number of particles per unit volume. Okay, that is 1 by centimeter cube. Okay. So here if you see now, now we are introducing absorption coefficient, that is mu a, and mu a is nothing but rho into effective cross section of absorption. Okay. So this is how it's defined. The mu is equal to the multiplication of number density into the effective cross section of absorption for a single photon. So it's like for a single molecule, and so it's kind of a multiplication of both of them. So we can actually say that this is eventually for a it's actually a bulk optical property. Right. Another way of another parameter that people usually use is the absorption mean free path. Okay, so that is also kind of used. So that is nothing but LA is given by 1 over mu A, right. So this LA is defined as absorption mean free path. Okay, so that is also meaning that the distance between two absorption event. So distance between the distance traveled by the photon before it actually gets absorbed. That's average distance. That is, so that's you would also see the earlier lectures that we have discussed about mean free path. It's similar to that. So amount of distance that is photon traveling before it's getting absorbed. It can go for multiple scattering events, but it would be the average distance that is traveling, the photon is traveling within the tissue. Okay, looks good. So now what we have done is that we have tried to find out the bulk optical properties, that is nothing but related to absorption. Now we need, so bulk optical properties are not just absorption, but there is also one more property that is known as scattering. So now let us see how do we quantify the scattering cross section and the scattering coefficient. Okay, so again for that we do the same analysis that we do earlier, that is you have a tissue constituents and that has many particles. Now instead of many particles over here, we try to focus on a single particle. So we try to take a single particle out of this and we try to see how the light interacts with this single particle, and then we move back later on by multiplying our results by number density to get the bulk properties of the tissue. Okay, so now let us see, you have this okay, let me see what color combination that I used. Okay, yeah, so for the particle I used green color, so let me choose, so this is a particle with a particular radius. Now I shine the light source or light beam, as you can see from here. Okay, now what will happen, as you can see, is that the top few photons will not interact with this molecule and it will directly get detected in the detector, right. Now as you go on further, so for example the third photon over here, it will interact with this molecule and it will move away like this. Okay, then one more can actually come over here, it can come over here like this right, and then one more can come over here and it, so there could be many more, something like this, and it will go something like this, and then it could make something like this. Okay, then it's straight, something like this. Okay, so again what do we see is there are two cross section. Two cross section means cross section of your of the sphere, that is this one that we have defined earlier, the same cross section, that is the area of your of the cross section of the sphere, that is a circle, right. So here this is defined as A, right, that is known as geometrical cross section. Okay, and then again what you see over here is the light actually which propagates through this molecule, that they get scattered in different angles. So what we actually come up with is is that there is like, this is the cross section of, so effective cross section. Okay, this is something known as effective cross section, this kind of circular cross section, right. So this is known as effective cross section again, but this is with respect to the scattering now. Okay, this is defined again as sigma, but now sub s. So in the it has a subscript s, which denotes for the scattering part. Okay. Now again, what we want to do is that we want to define scattering coefficient, right. So now to do that, I need to define my sigma s. So sigma s very similar to the power of the absorbed power. We defined some time back that absorption absorption coefficient, sorry, absorption cross section was a ratio of absorbed power by incident intensity. Similar to this, we have scattering cross section is given as scattered power divided by incident intensity. So PS is given as scattered power I naught is given as intensity of incident light beam. Okay, this is given as watt per centimeter square again. So here you take this watt and then you have denominator, you have watt per centimeter square. So what you eventually get is centimeter square, because watt and watt gets cancelled. Okay. Now this actually also has one more criteria. So it also is a function of the direction of where it is, the scattering is kind of sorry. So it has a direction where the power is getting scattered. Okay. Now I want to move from single particle theory, as I have discussed over here. From single particle theory I want to move back to a many particle theory, right. So how do we move back is that I just write this equation directly, that is mu s now is equal to rho, that is the number density, into the sigma s, right. So again, where rho is the number density and sigma is the scattering cross section. Okay, and then you can also define something known as scattering path length, or scattering mean free path, which is defined as Ls, which is nothing but 1 over sigma mu s. Okay, where Ls is defined as scattering mean free path. Okay. So this is how you actually go forward and define the bulk properties of your tissues. Okay. So just to summarize, what do we do? You have a tissue which is having many tissue constituents. So it has some of the tissues with very large diameter, another they have in smaller diameter. So it is something known as the tissue actually has it is a heterogeneous property. Right. For simplicity, what we do is that we make the tissue to be homogeneous. Okay, this is for simplicity, which means that all the particles would be having same diameter. So this is something known as homogeneous. Okay, and what is the aim? Our aim is to find the bulk properties. That is the most important, bulk optical properties. Now, why it is important to find the bulk optical properties? Because from this we can actually differentiate the tissue is having some issue or it's kind of normal. So because we know what is the bulk optical properties of normal as well as diseased tissue, right. So what are the bulk optical properties? It is nothing but mu A, that is absorption coefficient, and mu S, that is the scattering coefficient, right. So, first we have heterogeneous domain, tissue domain, and then from there we assume that it is a homogeneous domain. From this we actually tell that instead of many particles, we have a single particle, okay. So, we actually work with a single sphere, and then we try to understand what is the effective cross section. So, we talk about sigma A and sigma S, the effective. So, scattering cross section, effective cross section, as well as absorption effective cross section, and from there we again move back to our original theory of many particle system, that is now it has many particles with the same diameter. So, to do that I just multiply it by, so if mu A is there, I just multiply it by mu into sigma A, and then mu S is there, I just multiply the number density into sigma S, right. So, this is the approach that we take from to calculate the bulk optical properties such as mu A and mu S from the actual tissue property, heterogeneous tissue properties, okay. So, this is what I wanted to cover today on the cross section properties of the absorption and the scattering for different particles. Okay, thank you.